Bam! Mr. Tarrou, in this algebra lesson, we are going to continue our learning and gaining more understanding about solving linear systems. So far, we have created or developed those linear systems by reading word problems and extracting the information from them. We have learned how to graph those linear systems so that we can find out where those two lines are intersecting. The intersection point of those two lines is the solution to the linear system. And graphing is great. We like it. It helps explain that we are trying to find out where two lines cross. In, say, statistics, we do a lot of linear regression lines, using lines to model real-life data. And thus, if you have a couple different sets of data, we'd like to know where those lines are intersecting. But the fact that when you solve these linear systems, you might have two lines that are parallel, thus they never cross, thus there's no solution, or your book might be calling that inconsistent. They're either one solution where they're independent, there's no solution where they're inconsistent, or maybe it turns out that the two lines, the two equations you were given actually end up lining right on top of each other, kind of effectively the same line. Those systems are called dependent. We're going to, I don't think I've said it yet, I'm going to put links to those first two lessons in the description, and we will also be talking about solving these through a linear combination or elimination. I'll put a link to that lesson in the description as well. And we're going to go through 5 examples going from easy to hard. I'll put timestamps in the description if you want to skip ahead to one of those 5 examples if you don't need this whole lesson. Maybe you're just doing a quick review. 2 of those 5 examples, by the way, are going to be revisiting the word problems that we set up in the first lesson. So solve one equation for one variable. And by the way, you want to look for or choose to solve for one variable, or for the variable that has a coefficient of 1. You might have more than one variable in your system that has a coefficient of 1. You don't need to solve for every variable that has a coefficient of 1. Just pick one. So get that one equation, solve for one of the variables. If you happen to notice that none of the coefficients are equal to 1, then really the most efficient technique for solving that linear system is going to be the linear combination or the elimination method. But we don't have that in our toolbox yet, so we'll have to do everything with substitution regardless of what's in your homework at this point. Plug your expression answer from 1. We're going to have, x equals some blah, 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 y equals blah, 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 or some other variable. We will have, from step 1, one of the variables alone. It's going to be equal to something, but it won't be like x equals 2, except for this simple example in the beginning. It'll be equal to some kind of expression. And I probably should have wrote the word substitution there. Just wanted to make sure that we could fit this all in. But step 2 is really where you're bringing 2 equations and you're plugging them in together to make one new equation with only one variable. And that's really the substitution part of this process. And you want to plug or substitute your expression answer from step 1 into the other equation you have not yet worked with. It's very, very important. If you kind of like pick an equation, solve it for a variable, and then plug that value back into the same equation, you're just going to go around in a circle and not get anywhere. Solve the new equation for the remaining variable. After step 1 and 2 are done, you'll have a third new equation, and if you've done correctly, it will only have one variable in it. Plug the numerical answer that you get from step 3 into one of the original equations to find the other variable. We're finding out where two lines cross. We don't have to necessarily use the variables of x and y, but we are looking for an xy coordinate basically on the Cartesian plane where the two lines cross. Thus you need 2 numerical values. And then finally, check your answer that you get in both of the original equations. We talked about that when we were solving systems by graphing. We're looking for, again, where two lines cross, so that point needs to be a solution or be on both of those lines, not just one of them, and that's the phone. Sorry for the interruption there. So here we go. We're going to take one of these equations and solve it for one of the variables. And the tip was find a variable that has a coefficient of 1. So normally I would say, hey, this x has a coefficient of 1, which we don't necessarily write all the time in algebra because multiplying by 1 is the multiplicative, or 1 is the multiplicative identity for for multiplication. But I can look up here and say, hey, if I say, and let's number this in, put these steps in yellow. For step 1, I'm going to not exactly follow my suggestion. because if I take 3x equals 15, and just from number sense, remember or know that if I divide both sides by 3, that answer is going to come out to a nice integer, not a decimal or a rational value. So now I can take, and this will be the simplest example, it's the first one, my variable, I've now solved it and actually know that x is equal to 5. It's not x equals some kind of expression with numbers and variables mixed in like you will normally have with these problems. So step 2 is to substitute your answer from step 1 into the equation you've not worked with yet. Now, this 5 is equal to x. So I'm going to go up to that other equation, find where the variable of x is, and know that I'm going to take out that variable of x and plug in whatever it's equal to. So, down here at step 2, I'm going to do that substitution. And this is what I like to do when I teach my kids to substitute. I'm going to write that equation out, not even look at what I'm plugging in. I just know that I have something for x. So it's 1 and then x. X is a, variables are normally letters, sometimes words, but they're variables, they're letters that represent unknown values. Now that value could be a number or it could be another expression. But x is some unknown value, so it's something plus 2y is equal to 17. Well, that something that we're plugging in for x is 5. So I didn't write 5x, I didn't write 5 plus x, and all the other kind of crazy things that I see my algebra students do when they first start learning this technique. X comes out, and in its place goes 5. Whatever is on the right side of this equal sign, no matter how complicated it is going to go in place of x, not in front of it. Now we've got, normally we have a multi-step equation. In this case we have a two-step equation. Clean this up just a little bit and start remembering those steps that we learned about solving linear equations, multi-step linear equations. Multiply through the parentheses or distribute through the parentheses to, get rid of them. Combine like terms if there's any on the same side of the equation. If you notice there's a variable on both sides of the equation, you have to add or subtract to get those variables all to one side. A lot of times we default to the left. And then finally, we want to add or subtract away from the variable. So we have a positive 5, an addition of 5 basically, over here with the 2y on the left side of the equal sign. We're going to apply the inverse math operation. The inverse math operation to an addition of 5 is a subtraction of 5. And finally, we're going to divide both sides by 2 to undo that multiplication that's connecting the 2 with the y. Great. Now, the reason why you want to add or subtract away from the variable before you start worrying about doing any kind of division is if I were to divide both sides of the equation by 2, I would have 5 over 2, which is a fraction. Now it's just 2.5, it doesn't run on forever, but a lot of times with fractions, if you turn them into decimals, they can get run on decimals, and if that round off error is going to cause you to get a wrong answer. And you have another fraction over here of 17 over 2. So I would have created 2 fractions or decimals that I would have had to deal with as I finished the problem. Well, in this particular case, if I waited to divide by 2 until the last step, there was, it had integers, there was no fractions to worry about. So this is step 1. Take an equation, solve it for a variable. Step 2, substitute that value or that expression into the equation you haven't dealt with. All of this here where I'm solving the remaining variable is step 3. Solve the new equation for the remaining variable. And then finally plug the numerical answer from 3 into either one of the original equations and find the other variable. So we're trying again to find out where 2 lines cross. They should be, if there's a solution, they will be passing through the same coordinate. So it doesn't make any difference where you put this value of 6 in. Now normally, this is kind of, like I said, this is going from easy to hard, but yet this is actually a pattern that doesn't show up that often, and that can actually confuse kids. Hey, I did my substitution and I solved for the remaining variable, I'm supposed to take this y equals 6 now and plug it back into the other, or one of the two original equations to find out what the value of x is. Well, in this particular case, we already knew what it was because we didn't have an expression answer from step 2. We had that numerical value, and these two lines are intersecting at the coordinate 5, 6. Now, the really awesome thing about this particular type of problem is you can grade your own paper before you give it to your teacher. All you got to do to check that answer is plug it into each of the original equations. So our check, there's your first equation. We said x was supposed to be 5. Yeah, and indeed we got 15 equals 15. Now, is the coordinate of 6, 5, 6 on this second line? Does it make both sides of the equation equal when you plug in that value or those values of x and y? Bam! And indeed it does. On to example 2 right now. So here's our second example. We're going to solve the system of equations y is equal to 4x and x minus 3y is equal to 22. Step 1. Solve one equation for one variable. Now my second equation, x minus 3y is equal to 22, does not have, sort of a variable by itself. I have the x and y both on the left-hand side. The coefficient of x is 1, so if I were to start with the second equation, I would try and get that x alone. But my first equation already has y by itself. So I don't really need to do any work for step 1. It's pretty much already given. Okay. Now in my first example, in my first example, we solve for x first. Doesn't matter what variable you find first, x or y. It's that it's either starting with the equation that already has a variable by itself, or pick one of them and solve for a variable that has a coefficient of 1. So you don't create any decimals or fractions you have to carry through the rest of the problem because these are rather long. Here we have y is equal to. So we have been given a variable that's already solved for. Y equals whatever is on the right-hand side of this equation, which is the expression of 4x. Now, I don't know exactly what y is, like I don't know if it's 2, but I do know that it is whatever x is times 4. So we're going to draw a box around this 4x because it's like a stamp. And I'm going to go to, because this is the first equation, I'm going to go to the second equation, and let's see here. I like to draw pictures of what I'm doing, but then I have like spaghetti all over the board, kind of looks like, but maybe we'll do this. Something like that. I hope this is going to be clear to you. So for step 2, what I'm going to do is, this is the first equation. I'm going to focus on getting it substituted into the second equation. This 4x is equal to y. So in this second equation, wherever the y happens to be, the first term is x. Well, this is equal to y. There's my y right there. It's 3y. So when I write the second equation, I'm going to write, in yellow, I guess, because this is how I've started this here, x minus 3, and I've highlighted this in blue this time. Hopefully that's showing up on the camera. So it's 3y. It's 3 times whatever y I've gotten from the first equation is equal to. So the y comes completely out. Okay, this 4x is not going to go in front of y. A variable is a letter or word that represents an unknown value, or in this case, expression. So it's x minus 3, and now in y goes 4x. So you see, this is equal to y. I color-coded it blue, and in blue, in replace of y, goes what it's equal to from the first equation. So I have just put the first equation inside the second one. The first one went inside the second equation. I've created one new equation from the previous original two, and I've got an equation now that's only got one variable in it, which means that we need to solve this multi-step equation. So for step 3, we're going to, well, solve for x. So that means that if you have parentheses, you're going to distribute to those parentheses to get rid of them. So I highlight that in orange. Negative 3 times 4 is negative 12x. Notice I didn't write a plus or minus automatically. I did that multiplication first and to determine the sign of my product or my answer. So it is negative, so I'm writing minus 12x is equal to 22. We've got that equal sign breaking the left and right hand side of this equation up. I now have some like terms on the left. I have two terms are separated by addition and subtraction, that have the same variable. And a lot of my students do like to write those hidden coefficients of 1 so they can see that 1x minus 12x, well, if you're at 0 and you move 1 to the right and you move left for subtraction 12 units, your answer is going to be negative 11. What math operation, what's on the left-hand side with the x? What math operation is holding that number or attaching that number to your variable? Well, it's negative 11 times x. The inverse math operation of multiplication is division. So we're going to divide both sides by negative 11 and get x is equal to negative 2. Now, this is all step 3, the solving of the new equation for the remaining variables. Step 4, again, is to find the other coordinate of the intersection point. So, I've labeled this in terms of x and y. We've got the x coordinate of our x value of our coordinate. Let's go find the y. And one more time, we do that by plugging it back into either one now. We don't have to go into the other, new. Let's do this in blue again. It's not like before where we started with the first equation and had to plug into the second one. This is half of the intersection point. Both of these lines are supposed to be going through the same coordinate. That's why it doesn't make any difference which one you plug it into. And it seems like the first one is the easiest. So for step 4, we've got y is equal to, this x is negative 2, so it's 4 times something, that x, which is equal to negative 2. If I didn't use parentheses when substituting, you could put a dot for multiplication, but dots are really easy to miss as you reread your work. So I don't want that looking accidentally like 4 minus 2. It is 4 times negative 2. And the parentheses help to magnify the fact that there's multiplication there and not have you sort of, glance really quick and go, oh, that's right, 4 minus 2. Well, you just wrote 4 times negative 2. We want to make sure that we get that negative 8. And so the coordinate where these two lines intersect, we believe, is negative 2, negative 8. Now I say believe because I can make sure that's right by checking my own answer before going on to the next problem, which is what I'm about to do. So we're revisiting one of those word problems from our first lesson. Again, that link is in the description if you want to watch that. A rectangle's length is 2 inches, less than 3 times the width. Well, less than and more than, we understand that if things are becoming lesser, they're getting smaller. But when you have less than and more than in your sentence, as you write the expression out of that sentence, you need to make sure that you change the order. So even though 2 shows up in the word sentence first, in the algebraic expression, it needs to come second. So there's 2 less than 3 times the width. And so then we have information about perimeter being 28. Well, anytime a word problem gives you a number with a variable attached to it. Try that again. Anytime a word problem gives you a number with an equation attached to it, you can be guaranteed you're going to need that equation to help you finish the problem. And of course, the perimeter of a polygon is just adding up all the sides. And with a rectangle, you have two pair of opposite sides which are congruent. And that's why we just have the 2L plus the 2W. So I read the question carefully. I highlighted all the information that I thought was very important, and either you can write that information out in a list or just highlight it in a problem so you can use it to set up your equations. And I used to have a bad habit even as a math teacher of not doing this, but you need to get to the end of the question and look for what it's specifically asking for. What are those unknown values? Because that's what variables are. Letters or words that represent unknown values, and thus the question is going to tell you what variables you need for the problem and what the definition is. Please make sure you include that for your teacher. And now we've got, we're stepping up in difficulty. Now we had a word problem, but our first three examples all had that first step taken care of, which was take one of the two equations and solve it for a variable. Well, so that means that step one is already done. Now for step two, we're going to say, well, L is equal to 3W minus 2. So we're starting with the equation that is relating the length and width together. I guess you could argue they both are, but one's for the perimeter. Now I'm going to take this expression of 3W minus 2. The substitution part is always about taking the expression from one equation and putting it into the other equation, taking those two and bringing them together to make one new sort of third equation, if you will. It's just part of the solving process. So this is equal to L. I'm going to come through this other equation and look for the letter L and make sure that I know that this expression of 3W minus 2 goes in for that L, because that's what this expression is equal to. So it's going to go right there as we do our substitution. So we have 28 equals 2. L is a variable that represents an unknown quantity, so it's 2 times something plus 2W. And that something that is going in for the variable L after the first two, coming from the other equation, is 3W minus 2. And we're revisiting those steps that we practiced quite a little while ago now of solving those multi-step equations. You have an equal sign breaking up the two sides of the equation. All of our variables are on the right. We should be comfortable solving for equations, whether the variable's on the left or on the right. We're going to distribute to get rid of those parentheses. 2 times 3 is 6. Don't forget to write the variables with it. W. 2 times negative 2 is negative 4. I didn't write negative automatically or minus. Oh, by the way, if I said read that out loud, you would say negative 4. If I put something in front of it, you would say minus. So really a negative sign and a minus sign are kind of the same thing. Your scientific calculator might disagree, but for writing out these algebra expressions, 2 times 3 is 6, 2 times negative 2 is negative 4, and that's all that we have inside the parentheses. So we're going to just bring down the 2W. Distribute to get rid of parentheses, combine like terms. On the right-hand side, we have a constant of 4. There's no variable attached to it. It's just the only constant on the right, but we do have two terms with W's. So we have a positive 6W and a positive 2. That negative is for the 4. Don't let it distract you. We're going to add those like terms and have 28 is equal to 6. Positive 6 and positive 2 is 8W minus 4. I'm not trying to move the 2W from the right-hand side of the equation to the left, so I'm not changing this plus 2W to a minus 2W. The 6W and the 2W are already on the same side. You're just going to combine them using whatever signs are there. Again, 6 plus 2 is 8. Now, on the right-hand side, we need to start moving away from moving numbers away from the variable of w, and as we cross over from one side of the equation to the other, in this case right to left, we want to apply those inverse math operations. So we have a minus 4 on the right with the w. We're going to apply the inverse math operation, which is addition. We have 32 equals 8w. What's left with the w? We have 8. So what's the inverse math operation? It's multiplication, it's division. So we're going to divide both sides by 8 and get 4 is equal to w. Now that all, I didn't label it, but all of this solving for the remaining variable after we bring the two original equations together is step 3. Now step 4, take this answer and plug it back into either one of the original equations. We have this one and this one. Looks like that if we want to find the length, this equation already has L by itself, so that would be the easiest equation to plug our W equals 4 into. And I guess we'll highlight this one in blue. Don't think you're going to see that blue and the green separated, but hopefully you can follow along what we're doing. We have the length is equal to 3 times our W value of 4, right? That's what we just found, minus 2. 3 times 4 is 12, minus 2, and that is equal to 10. So if this checks out, and I'll put that check up there before we go on to the next problem, we have a width of 4, or W of 4, and an L of 10. When you are doing solutions, when you're solving word problems, I am sure your teacher is going to require you to write your solutions, summarize them in the context of the problem. So I need to make sure that I write down exactly what this 4 and this 10 is. The rectangle is 4 inches wide and 10 inches long. So now I've summarized my solution in the context of the problem. Do a quick check and get on to our next example. Bam! Last word problem. You have $300 to spend on shirts and pants. If shirts cost $23 and pants cost $35 and you leave with 11 items, how many of each item did you buy? We thoroughly went over this problem coming up with these equations on our first lesson, and we actually just solved this in the previous lesson, solving linear systems with graphing. So this time I'm just highlighting the important information and writing that out. We have an equation for money, and we have an equation for the number of items. $23 times each shirt you buy, plus $35 times each pair of pants you buy, coming up with a total of $301, along with the fact that we bought those 11 items. Getting to the end of that question, where it says how many of each item did you buy, that final question is what helps you define what the variables are. And this time, we don't have an equation that is solved for a variable already. But we do have an equation where we have some coefficients that are equal to 1. So I can start this problem by solving the second equation for S or for P. It really doesn't make any difference. Now, I do want to follow my notes in case I need any arithmetic help, because I'm doing this on the camera without the aid of a calculator. And the first time I did this, I went ahead and took the second equation. So for step 1, we're going to take one equation and solve it for one variable. So I'm going to pull the S plus P is equal to 11 out and solve that for one of the variables by subtracting both sides by S. I'm going to try very hard to make my S's not look like 5s, which they often do. When we were doing this, when we were solving this linear system by graphing, I made sure to keep this sort of in slope-intercept form, where it's sort of in a form of like y equals mx plus b. But in this case, we're just going to do substitution, so it's not really, not that it is really a big deal when you're graphing lines either, but in this case, I don't really care if the constant is first or second. We're going to, let's see, I guess highlight this in orange, or some color I haven't used yet. How about green? We're going to recognize now that we've got an expression of 11 minus s equal to p. And we've already started working with the second equation. So we're going to plug this expression of 11 minus s, which is equal to p. So I'm going to come up here on the first equation and see that letter of p, and that's what is, well, that blue and green almost look the same. But that letter p is going to come out, and in its place we're going to put 11 minus s. And this is step 2, where you're bringing the two equations again together to write one new equation that only has one variable. So we've got 23s, just copying down what the equation says because I'm worried about getting to the variable of p, plus 35. Now, because I'm plugging this expression in for p, I'm going to put a set of green parentheses there. Hopefully you can see that on the camera. And in place of p, not in front of, not behind, not going to have the letter variable p somewhere mixed in with this equation. P comes out, and in its place is 11 minus s. And then just copying the rest of the equation. We again, and this happens a lot with solving systems of equations with substitution method, we get these kind of lengthy multi-step linear equations. So once again, like we've talked about before, we're going to find some blue chalk, I guess, and multiply that value that's touching or in front of the parentheses, multiply that through the parentheses. We have 23s. We have 35 times 11. Now 35 times 10, that's the tens place, is 350. And then we have 35 times 1, which is another 35. So 350 and another 35 is 385. And then, whoops, that's a bad, don't ever do that. I wrote a plus sign before actually doing the math. Don't figure out, a plus or a minus until you've actually multiplied. That's a positive 35 times a coefficient of negative 1s. So it's negative 35s is equal to 301. Just make sure that really was 385. Yes. Let's go ahead and combine like terms. So we are looking at, now I just about said that was 335. That's why I try and avoid the variable s, but then I did include it in my problem. We have two like terms. Those like terms, again, having those same variables and the same exponents on those variables, or the same number of that variable. We have 23 minus 35. Well, when you combine numbers with different signs, you want to subtract those numbers and keep the sign of the largest absolute, why am I doing that? The largest absolute value. 35 is larger than 23, but it's actually negative. So our final answer is going to be negative. 35 minus 20 is 35 minus 20 is 15, and 15 minus 3 is going to be 12, but it is negative. Now we're going to subtract both sides by 385 to undo that addition, giving us negative 12s is equal to, okay, again, this is going to be a negative answer because we are combining a positive with a negative. And when adding or combining numbers with different signs, you subtract. 385 minus 300 is just simply 85, and then 85 minus 1 is 84, but it is negative. And we're going to undo that multiplication of 12 that's with the s by applying the inverse math operation, which is, oh, I didn't highlight my scratch work in blue, division. And s comes out to be 4. So we took one of the equations, solved it for one of the variables, look for those coefficients of 1, take that expression, plug it into the other equation. It was equal to p, so it went in for p. And then we did step 3 without labeling it, which is solve for the remaining variable. Now step 4, as I write big enough so that you can see it and thus run out of room, is to take that numerical value and plug it back into one of the original equations. I think I'm going to pick the second one because it's obviously the easiest with the smallest coefficients. So Oh, we've got lines, like I said. My substitution problems always end up looking like spaghetti, trying to point to what I'm doing here. So s is equal to 4, s, which is equal to 4. Now, plus p is equal to 11. Solving this for p, subtracting both sides by 4, we get p is equal to 7. And once again, this is a word problem. I'm going to go ahead and skip the checking your answer this time. It's really the third time over these lessons I've actually solved this, I think. But we do need to summarize, so I know that those are the answers. I do need to summarize this, though, in a full sentence. So you purchased, what? 4 was S, so 4 shirts and 7 pair of pants. And there is the summary of these numerical values that we got from our algebraic work in context of the word problem. Got 2 more examples coming up. I think there's just 2 right now. For our last 2 examples, we've got they kind of actually a little bit simpler. We're getting out of the word problems. And this one kind of isn't really a linear function because we have an equation here with 3 terms, not just 2. But again, just the idea that you got a system of equations. This time it's 3 variables or 3 unknowns, thus you need 3 equations. Almost always you need as many equations as you have variables. Rarely they'll factor apart into 2 separate factors, but you'll get to that later in your algebra studies, I'm sure. Right now, as I go to try and solve this 3 variable 3 system equation, you could use your number sense to come up with some possibilities, but when you have equations that have 2 variables, there's more than likely a lot of different combinations of those 2 variables that can make the 2 sides equal. Indeed, there's an infinite number of solutions to y equals negative 3x plus 1. It's a line. It's made up of an infinite number of points. It's a line with a y-intercept of 1 and a slope of negative 3. So if a line is consists of an infinite number of points, each of those points having an x and y coordinate that makes the 2 sides of this equation equal, there's an infinite number of possibilities. So you want to go to the equation that has just 1 variable. That's the first one. So if we pull 2x equals 12 out to the side and say, well, let's go after that. With the x, you have a multiplication of 2. The inverse math operation to multiplication is division. So you divide both sides by 2, and you get x is equal to 6. Okay, great. Well, now what I'm going to do is I'm going to take that 6, go into my other 2 equations, and anywhere that I have a variable of x, I'm going to substitute in the value that it's equal to, which is 6. Now, students will often do substitution more accurately when they're just plugging a number in as opposed to an algebraic expression, but it's just the same idea. Out comes the x, in goes what it's equal to, and out goes the x, and in goes what it's equal to. That was negative 3 times x, so it's going to be negative 3 times 6. Well, now I'm going to look through, well, and of course we already know that this is x equals 6 there. You can double check it. 2 times 6 is 12. Yep, 6 is a solution. And now what equation only has 1 variable in it? Well, now it's the third equation. So maybe I'll pick green and say, okay, well, we have y is equal to, well, negative 3 times 6 is negative 18 plus 1. So we know that y is equal to negative 17. And now, since the only equation left that I haven't worked with is the second one, I'm going to take that value of negative 17, plug it into that second equation, the only one that has a variable that's unknown left in it, and recopy it again, replacing the variable of y with what we now know that it's equal to, which is negative 17. So that's going to look like this. We're going to have 6 minus, and I'm putting a set of parentheses in place of y. That open, that's all a variable is just an open place. They actually call these open sentences because there's variables to plug values in for them. minus 2z is equal to 7. Now, if I do that, I basically just, again, copied the equation 6 minus y plus 2z equals 7. Knowing that I'm plugging something in for y, I just highlighted the fact that it's 6 minus something that y represents, minus 2z equals 7. And why am I making a big stress about this? Because y happens to be negative 17. Well, if I wrote with part of the chalk that was a little bit thinner, you could read that. And a lot of students, when they're first starting off in algebra, will they'll get confused in the fact that there's a negative sign in the equation or expression you're plugging into, and there's a negative sign with the number, and they'll end up only writing one negative sign, but there is a negative from the equation that we were plugging into and another negative from the numerical value that we're plugging in. And if you don't include both of those, well, then you're going to get the wrong answer because, again, we don't generally write coefficients of 1 because it's the multiplicative value for the multiplicative identity. When you multiply by 1, nothing changes. But if you slip that 1 in there, you realize that minus a negative number really is 6 minus 1 times negative 7. And when you multiply two negatives, you cancel out and make a positive. And that's how the two negatives side by side cancel out, make what we just kind of, a lot of times you just write sort of like a plus sign through there to kind of go, yeah, it looks like a plus sign, and it is. It's really negative 1 times negative 17. Now we got 6 plus 17 is 23. And I'm going to do something that I really hate having to do, but I'm running out of room. I didn't like that as a kid when I was taking notes anyway, so apologies for having to do that. With the z on the left, we have a addition of 23, so we're going to apply the inverse math operation, which is to subtract both sides by 23. And negative 23 plus 7. If you're at 0 and you move left 23 units and back 7, you are going to be at negative, 16? And then divide both sides by negative 2, because with the z you have a multiplication of negative 2. Those inverse math operations cancel out. Anything divided by itself is 1. So 1z is equal to 8. And we have all three of our solutions. Now, the video is getting a little bit long, so I'm skipping the checking part, but of course, we can take these values, we can plug these values back into each of these three equations and make sure that the two sides are equal. I'm going to glance at my notes and make sure that I got the same answers as I did before. Something seems to have gone awry. This is actually why you check your work. I'm actually talking myself into showing you guys why you want to check your answers when you're done. I've already done the numbers, plugging them back into these three equations, which I almost skipped over. I am going to, again, not include that to shorten up the video a little bit, but do you see the mistake I made? I'm unfortunately very susceptible to this even after 21 years of teaching math. It was my scorn as I went through school as well. You probably were noticing as I was teaching. That's 6 minus y plus 2z, and I wrote basically 6 minus y minus 2z, so this is actually the wrong answer. Now getting my red pen out, which is my red piece of chalk, yeah, Mr. Tarrou, you made a sign error, and we're going to have to mark a point off of your work because you carried that, the only mistake you made, but you did carry it through the rest of your work and thus got the wrong answer. But we caught it because we checked our work, and the teacher doesn't have to take off that point. You can fix it yourself and get full credit. Now over here, we have another situation where we have a substitute. We could do this with linear combination or elimination in the next video, but for now, we only have our substitution techniques available to us. So we're going to take this first equation, so for step 1, and write 3y is equal to negative x. And we are going to solve this for x by getting rid of. Alrighty, so we've got to divide both sides by negative 1 to undo that multiplication of negative 1. And we get negative 3y is equal to x. And you've seen this many times now. So let's just pick up the pace a bit. We've got x is equal to negative 3y. Now that we have that one equation solved for one variable, it is going to go into the other equation, which we have not worked with yet. And we get, in step 3, making that new equation with the combination of the two original ones, we have x. Okay, that's what we're plugging into. So x is some unknown value or expression plus 3y is equal to 21. Okay, now that x that we're plugging in is equal to negative 3y. And as we start to solve this multi-step equation, on the left side of the equal sign, we have negative 3y plus 3y. Well, negative 3y plus 3y. Well, negative 3 plus 3 is equal to 0. It seems kind of weird. That's not right, right? I mean, I'm supposed to solve for x and y. There's probably supposed to be a y there, right? Y is 21, and we'll continue the problem. No. If you write a variable, if something weird happens and you're like 0, well, that must just be y. Well, then you're saying that you have, remember, 1 is the multiplicative identity for multiplication. So if you get 3 minus 3 is 0, and then write y, what you're actually saying is negative 3 plus 3 is 1. No. Negative 3 plus 3 is 0, and anything times 0, the zero product property rule, says is equal to 0. So here we are just going along our business, minding our own business, trying to solve all these algebra equations, and we get to a point where all the variables just sort of disappear. And what you get is a false statement. Well, again, remember I said that we've come up with the linear systems from word problems. We solve linear systems with graphing, and it's very easy. This is the same problem we did in the previous lesson. Again, link in the description. And when you're graphing these systems of equations, it's easy to understand how there can be no solution. You have parallel lines that don't intersect. Algebraically, what happens as you're doing that problem, when you get, what's it called, an inconsistent system, parallel lines that don't intersect, or when those, it looks like you're given two equations, but they actually end up sort of graphing right on top of each other, they're the same line, that's an inconsistent system, and this is called a dependent system, where the two lines are the same. It's no solution, or it's an infinite number of solutions. Well, if you get a false statement, those are, the reason why that's happening is because you're trying to find the solution between two lines which are parallel. Now, your teacher might not need you to say that you recognize that you have parallel lines, but what you do need to say is no solution. Or if your textbook is using this vocabulary, you would say that that system is inconsistent. If we had gotten to this point and it was something like 21 equals 21 or 0 equals 0, whatever, if all of your variables fall away and you're left with a true statement, well then that's a situation where your two lines are actually the same line, or there's two lines laid on top of each other. That's an infinite number of solutions, or what you'd call a dependent system. I'm Mr. True. Bam! Go do your homework.